This question is about the mechanical energy that is possessed by an object due to its motion or due to its position. Note that mechanical energy can be either potential energy, which is the stored energy of position, but another energy named kinetic energy, which is the stored energy of motion. Between these energies, one form of energy is transformed to another form of energy in that object is currently referred to. Since on this problem we focus on this scenario, whereby this trolley weighing 540 kilograms is moving to the right to point B from point A with a velocity of 12 meters per second, then it comes to the rest on point C. A to B is a rough surface, which means it has been experiencing friction, whereby we are only given a coefficient of friction to be 0.8. The incline B to C took an incline of 7.5 degrees up from the ground or surface, and it is said to be a frictionless surface. We are given the length of B to C to be 4.5 meters long. This length makes things easier for us to get the height of point C. We introduce the horizontal component from point B to point E. This point E is from our labeling. That horizontal component is 4.5 cos 7.5 degrees. Then we introduce the vertical component, which is the line from this point E to this point C, and remember this is the height we are looking for. The value of this height will help us throughout our calculations wherever it's necessary. This vertical component is 4.5 sin 7.5 degrees, which we equated with h for the height. On 8.2, we are requested to calculate the velocity of the trolley at point B. When we apply potential and kinetic energy on point B, the potential energy becomes zero, that is because of the position where the trolley is, the height is zero. And on kinetic energy, the velocity is what we are looking for. Then on point C, we have a height, which means the potential energy on this point C is not zero. But as it is said that on point C it is where the trolley rests, of which means, on this point the velocity is zero, that makes the kinetic energy to be zero on this point. So, on this conservation of mechanical energy formula, at point B, we are left with kinetic energy with velocity as unknown, and at point C, the potential energy remains with no unknown. On this step, we make velocity a subject of this equation. Calculating this, we get this number as a value of the velocity of the trolley at B, which is measured in meters per second. On 8.3, we are instructed to calculate this frictional force value that happens between point A and B. To get frictional force value, we say, frictional force equals coefficient of friction times normal force, whereby this normal force is mass times gravitational acceleration constant. That will be 0.8 for the coefficient, mass is 540, and the constant is 9.81. Calculating this, we get this number as the value of frictional force, which is measured in newtons. On 8.4 work energy theorem, it is just net work done which is equal to change in kinetic energy of the object or body. That work energy theorem, we apply it on 8.5.1 to get the work done by friction between point A and B. In that formula, we use this velocity 12 meters per second as initial velocity, and this velocity of point B as a final velocity. Calculating this, we get work done by friction to be this number, the unit is joules. Since the distance between from point A to B is not given, now we are instructed to calculate it. We apply the work done by friction equals frictional force times change in length. Work done is this value, frictional force value, and as for this cos theta, because this segment A to B is a straight line, that is 180 degrees we use. We have only this change in length that remains unknown. Calculating this, we get this value as a change in length.